quickly time.
Yeah, we are live on YouTube.
11 o'clock on a fourth Sunday. Yes, we know it's a fourth Sunday. It's not the typical Chai and Wai Sunday, but it is Azadi Ka Amrit Mahotsav, and thought this is a good opportunity for us to do a special Chai and Wai, from the Semiconductor Optoelectronics Lab at TIFR, where we'll try to tell you what we do here. What's this big blue box behind us? And with me is Manisha. Hi, Manisha. Manisha is a PhD student who works on this system here and works in our group. And there's also Rahman, who is behind the scenes and helping with a lot of things. There's Rahman, and of course, there are a lot of people back end online to answer questions on YouTube or Zoom, wherever you're watching. Now, we can't see you. It's a pity. So, the only way we have your feedback, we know what you're asking us, we know what questions you have, is if you enter them on your chat. So, if you're watching on Zoom or YouTube, please use the chat to enter your questions and comments, and we will take them either during the show or at the end. We will definitely take as many questions as we can. Okay, so let's get started. This is the Semiconductor Optoelectronics Lab at TIFR.
Hey, before we get into what we are doing in this lab, I think maybe we should tell the audience what semiconductors are and what optoelectronics.
Good idea. We should tell them what semiconductors are and what optoelectronics are. Let's start with electronics itself. Have you seen something like this? Manisha, do you know what this is? The thing I'm holding in front of the camera?
I think we can. It's a circuit board. So I think we can ask the audience what it is made of.
Okay, so this is a circuit board. This is the motherboard for a computer. I took it out, and on these boards you find lots of these printed circuit board cards which have these chips on it. You can see these chips. Okay, so yeah, Manisha, do you know what these chips are made of? We should ask the audience. Audience. Why don't you put in the chat what are these chips made of? These chips that you see, these semiconductor chips which are there in these boards, or even on the motherboard. What are all these chips made of? So let's see what are people putting on chat. So folks who are looking at the chat, please tell us. Somebody just read out what are people saying. We'll give them a little bit of time. So what are people saying on YouTube? What are people saying on Zoom? Anyone? Is it?
It's a semiconductor.
It's a semiconductor. Okay, great. That's correct. These chips are made of semiconductors. And do you know which material is used as a semiconductor?
They're saying silicon.
They're saying silicon. Okay, that is correct. That is correct. Most of the semiconductor world is made of silicon. And silicon is great. Silicon allows you to make these transistors, make all these chips. You can make various things, computers, electronics, radios, TVs. All that is the world of silicon. Silicon is also very important because you can use it to make solar cells, right? Here's the solar cells. Here's a solar cell, and we have three little LEDs over here. And let's see if they're not glowing in the room lights, but we have some really nice and big, good old lights over here. So Manisha, do you want to turn it on? Okay, and now you can see these. Well, you can't see these, but maybe what we can do is we can cover this a bit. Yeah, you can. But you could have showed. Okay, turn it off. Turn it off. Did you see the top three little dots? They went on and off. Turn it on again. So look at the dots over here. Yeah, you can see a little glow coming. Those were the LEDs we had connected to the solar cell. So silicon also makes solar cells, and that's another very important aspect. We want to cover it today, of course. Have you ever wondered what is inside one of these chips? One of these chips, what is inside? I'm just going to show you. These are very old things. TIFR actually started silicon work in India in the 1970s, and I still have stuff in the lab. Can we enable chat for the audience? Why is it not enabled? Please enable chat for the audience. Whoever is the YouTube, chat on YouTube or chat on Ulhas, can you check if chat is enabled on YouTube? If it's not, please enable it. Anyway, while we do that, yes, somebody has said germanium is also a semiconductor. That's correct. I'll come to it in a second. But these are what these shiny things are, what silicon wafers look like. And when people make circuits out of this, what is inside the thing is actually, oops, it's so shiny that you can see the reflection. Let's see if I can, yeah. This greenish thing that you see, a lot of small things in it. That is, yeah, there you go. That, let's focus. Come on, focus. That is what is inside one of these little chips, but that's again not what we are doing, not what we're going to do today. There's something called opto. Remember, I said opto. Opto comes from optics or light.
So silicon is used for optoelectronics.
Silicon is used for solar cells. Silicon is great at absorbing light, but silicon doesn't emit light. So if you want to make something that emits light, something to replace the bulbs, tube lights, CFLs, right? Then you need a different material. Okay, I won't explain right now. Maybe in the end, if somebody asks why does silicon not emit light, we can look at it. But okay, I can't see the chat, right? So somebody, if there's something interesting happening on the chat, please let me know. Or the Q&A box in chat, both of them.
Yeah, if there is something, I'll stop you. Or
okay, if there's something interesting, please.
Yeah, we'll stop. We'll interrupt. Yes.
You keep saying semiconductor. So maybe we can ask audience what a semiconductor is.
Okay, good question. Yes, we should absolutely know that the audience is with us. I see somebody saying their name says 7A on it, so I assume they're in the 7th standard. So I hope you've heard the word semiconductor. Maybe you can put in the chat what is a semiconductor. Okay, do you know what a semiconductor is? If you've heard of conductors, insulators, semiconductors. Okay, so just put in the chat if you know what a semiconductor is, and then I'll try and tell you, what a semiconductor is and how things, current flows in a semiconductor, etc. But let's take 30 seconds to give people. Let me see if I can just log into YouTube here so I can look at the chat myself. I can join on Zoom, so. Wait, let's see what the. I'm just going to join on my phone so I can see the chat, because I cannot see the chat on the screen over there.
It's resistance between conductor and insulator.
Okay, just a second. Let me.
There is another comment. Semiconductor is a type of material whose band gap is less than an insulator but higher than a conductor.
Oh, that's so fantastic, Ankit. That's so fantastic. And Shivani says that its resistance is between a conductor and an insulator. Substance with a band gap. Mohit says band gap at high temperature resistance gets better. What's better, higher or lower? Okay, don't worry. You guys are all correct. That's me. Okay. It says chat is disabled. Ulhas, can you please enable chat? Can you please enable chat for the
I think there is some policy decision higher up for such events. I'm
okay,
afraid.
So I'll tell you what. Just make everybody a panelist. Just upgrade everybody on the Zoom to a panelist, so they can ask. They can put things in chat.
Okay.
Because
right.
we need interaction, right? I see chat is disabled. I can't see it here because it's disabled.
I'll make everybody a panelist.
Yeah, just make everybody panelist, and that will take care of it. I don't think there are too many people. Okay, so already I think you're seeing screen now, and let me just say that. Okay, so let's start with the periodic table. In the periodic table, if you notice that, there are what we said was semiconductors. This is silicon and germanium. These were in what is today called group 14. They are in today what is called group 14. Earlier it was called group 4. So these are the materials. And, you must have heard, people are talking about bands. So in case you don't know what a band is, let me tell you. So when you have, suppose you had just individual atoms. Individual atoms have energy levels. There's some lower energy level, higher energy level, still higher energy level. There are energy levels. Now, when you bring, that's for an isolated atom. When you bring many, many atoms together, so that's what happens when you make a solid, you bring many atoms together. When you bring many atoms together, if you bring 2 atoms together, the individual thing, they'll become a double. If you bring 3, they'll become 3 more. When you bring millions and billions of atoms together, remember that solids have 10 to the 23 Avogadro's number kind of atoms. Then you don't see these individual levels anymore. They all get mixed up and they form something called a band. And depending on the energy the electron has, some of these bands have lots of electrons in them. Some of them are completely full. If it's completely full, there's no space for another electron to go in there. Sometimes the band could be completely empty. In which case, if I put an electron there, it can travel because there's lots of space in that band. And sometimes there are things with it. Now, what is the energy difference between these bands is what is important. If the energy difference is very large compared to what? Well, we live in the world which is bathed with light from the sun, and a very good comparison is the energy that light has. And as somebody in the chat already has said, if you know what an electron volt is, semiconductors are materials which have, 1, 2, few electron volt difference. An insulator is very large, maybe 10 electron volts or more. So the chance that at normal conditions, there are many electrons that can go up and, be free and can conduct electricity is very small. Okay. In a metal which conducts a lot of electrons, the band gap is 0. Lots of electrons available for transport. Okay, so this is how it is. Very hand waving. I haven't done any of the real the physics explanation of it, but I hope this gives you an idea that there are bands, and because of this, because of how many electrons are available to move, the resistivity is different. Now, somebody said resistance is in between. Remember, resistance is something I can control. If I take copper wire, I take a small bit of wire, it's got very little resistance. But if I take 1,000 kilometers of that wire in a big bundle, it will have some resistance. So resistance depends also on the length and the area, lots of other things. What in physics people mostly refer to as resistivity. How much resistance per some area that the current is flowing through. But don't worry about it. The idea is correct. Well, let's go on. So we know what a semiconductor is. But remember I said silicon doesn't emit light.
What kind of semiconductors do we use?
Yes, what kind of semiconductors do we use? What would emit light? You know what? We have to make artificial materials. Artificial materials. So
how do you make such materials?
How do we make? We make it in this big box, but before that, let's see what are the materials we make. Okay. So again, what you see on your screen is a part of the periodic table. Now, you will call it group 13, 14, 15. When I was in school, there was still group 3, 4, 5. Most of the people who, the people who started this field of research, when they were doing their research, it was also called group 3, 4, 5. So we'll just refer to that. So now, remember carbon, silicon, germanium, all these materials are in group 4. Imagine I can take, so germanium is sitting here. To the left of germanium is gallium. To the right of germanium is arsenic. If I take one atom of gallium and one atom of germanium, I can sort of make a structure which resembles one atom of gallium and one atom of arsenic. I can make a structure that resembles germanium. So if you take an element from group 3, this is, the boron, aluminum, gallium, indium group, and an element from group 5, the nitrogen, phosphorus, arsenic, antimony, that group, you combine these materials, you can also make materials which are semiconductors. Of course, these are not elemental semiconductors. These are compound semiconductors because we're making a compound of elements. And the beauty is that, okay, these, of course, they're called, first thing, they're called 3, 5 semiconductors because we've taken one element from group 3, one element from group 5. So average is still somewhere near what, a structure like silicon, properties like silicon. Of course, they have different band gaps. everything you make, whether you take gallium arsenide, indium phosphide, aluminum nitride, gallium antimonide, everything will have a different band gap, and all these materials emit light. That's what we were looking for. We were looking for materials that emit light. So now if I make these artificial materials, they will emit light.
So are you talking about doping?
No, not yet. We'll come to that. Just a minute. Now, okay, let's stop this. We go back. So, the beauty of it is not that we have just gallium and arsenic or gallium and nitrogen. We can make mixtures. So if I have gallium and arsenic, the band gap is somewhere just in the infrared region. If I remove some of the gallium and put aluminum, the band gap goes up, it will move towards the visible region. If I replace some of the gallium with indium, the band gap gets smaller, it will move in the infrared region. Similarly with gallium nitride, which is the hero of the story, this is what we do over here. Gallium nitride has a band gap just in the ultraviolet, which is why if you have a vapor of gallium nitride, right? Gallium nitride, the energy difference, that imagine if the band gap is this much, and I shine light whose energy is less than this, the energy is less than this. It's not sufficient to take an electron from here and move it up there. So that light will just go through without doing anything. It will effectively be transparent. So materials like gallium nitride are actually transparent. We'll show you this thing. We'll show you this thing later. Materials like silicon, where the band gap is less, they absorb light, so they look shiny like this. What we can do? We can start with gallium nitride, which has a band gap near the ultraviolet. Indium lowers the band gap. Keep adding indium, you get to the blue. Add more indium, you get to the green. You can do this. You can play with this. It's like making khichdi. In making khichdi, what do? Start with rice and dal. Standard. Okay. Now, everybody's khichdi, how do you change the taste of your khichdi? Somebody would add more salt, more chili, more ginger. You like cooking, right? Yeah. So, you add this and the taste changes. Similarly, you start with gallium nitride. You want to make UV LEDs for water purification. You add aluminum. You want to make blue LEDs. You add indium. So you start with something, add little bits of other material. Now, what you said about doping, that is a very important word. Now, doping is very bad if you're in sports, right? You don't want doping. Those Olympic guys get caught and they get disqualified and all that. Now, that's bad. That doping is bad. Okay. Doping in semiconductors is wonderful. We love it. We absolutely love it. Because that is another very, very important part of semiconductors. I said that they need to carry a current. Right? A piece of silicon by itself, or gallium arsenide or gallium nitride by itself, well, yes, they can carry a small amount of current. But semiconductors are these amazing materials where you add a very, very tiny bit. How tiny? Maybe one atom in a million, or one atom in 10,000, or 100,000. 1 lakh atoms, you add one extra atom of another element. So in silicon, we would add maybe boron or arsenic or something else. In gallium arsenide, we will add silicon or zinc. In gallium nitride, we add silicon or magnesium or something like this. We add very little bits. Very little is 1 atom in a lakh or 1 atom in a million. And guess what? The way they conduct electricity changes. They can suddenly become, almost good conductors. That's really important. Because it allows me in a semiconductor to control this conductivity by just playing around with very small amounts of impurity.
So you are telling if you add more of this impurity, then that also changes the conductivity.
Yes, absolutely. Which means now, if I want to make these things, remember, 1 atom in a lakh or 1 atom in a million will change my properties. So I don't want anything, it has to be extremely clean. So you want to have materials which are like, 99.999999, many nines, that pure.
Oh, so do we have that pure elements?
Well, yes. We do have these pure elements with us, but that's not what we do here. Okay, so how do we make these materials? Okay, so let's there are two ways. There is another way, which maybe there's another lab coming up in TIFR. Maybe one day we'll do a session from there. What you can do, just imagine that I'm going to start. I want to make gallium arsenide. Okay, so what do? I take a big chamber. Okay, now I put something on it. Of course, when you remember, we have to. What we will do, we deposit gallium atoms, arsenic atoms, and make gallium arsenide. So we will deposit on something. So we'll keep that something. It's called a substrate. Don't worry, we'll show you. So something like, I'll keep this and I'll put my gallium atoms and arsenic atoms on this. Now, how do I do it? I take a big chamber and I remove all the air from it. I create a vacuum. Not any vacuum, not like, you create a small vacuum and you suck a drink with a straw, or, you must have seen some puff, in the vacuum cleaner, it has some. Those are maybe, they get to 1/10 of an atmosphere. No, we are talking about very, very high vacuum, because you don't want any other materials to be around, right? You don't want any other atoms. So you go down to something like, what is called 10 raised to minus 10 or 10 raised to minus 9, one atom, you remove of the billion atoms there, you remove all except one. That would be the kind of thing. Something called ultra high vacuum. And then if you have a chamber which is ultra high vacuum, you can start with very pure gallium, very pure arsenic, heat them up, boil them basically. A little bit of the vapor will go up on these gallium atoms, arsenic atoms, will come and deposit. This is one way of doing it. But it's not easy to make huge chambers which are, you remove all the air from it to get this extremely pure gallium, extremely pure arsenic. Very difficult. So that's not what we do here. This is something else. We use chemistry. You like chemistry in school? I hope you like chemistry in school. Chemistry turns out to be very useful. So I am a material scientist. I'm in a physics department, but this machine, it effectively does chemistry. Okay. This is called a chemical vapor deposition system. CVD, chemical vapor deposition. It's also called a vapor phase epitaxy system.
Oh, that's a new word. What does it mean?
Epitaxy?
Yeah.
Well, it's a new word. It's a new word for you, maybe. Epitaxy is very simple. It means you have something, you deposit things on it, not some, throw anything on it. Okay, you deposit things layer by layer. So I deposit a layer of atoms, another layer of atoms, another layer of atoms, another layer of atoms. We have the ability to do these chemical reactions so that they deposit the material atom by atom, layer by layer. Okay. So this is where we grow the semiconductor material. Remember, the title was growing semiconductor materials.
Oh, so this. Then what is this growth? Like you were telling this part.
Yeah. So how do you grow? You have cells. The cells divide and they multiply. That's how living things grow. Okay. This is slightly different. Here, what we are doing is we are growing a crystal. So these things are also crystalline materials. So we deposit atoms, one layer, another layer, another. So it starts becoming thicker, thicker, thicker. That is the growth that we're talking about. Okay. So this is the growth, and the growth is what happens over there. And the way we do it, hang on, not here. We'll give it a minute and then I'll show you what we're doing. So now, of course, let's say I want to grow gallium nitride, right? That's what we're doing here.
Yeah.
Now, I don't want to start this gallium metal and nitrogen atoms. Right? So what do we do here? I want to do a chemical reaction. Okay, chemical reaction. So what I will do is I'll start with some material that has gallium inside. Okay? And I'll start with another material that has nitrogen inside.
But why don't we just start with gallium metal?
Because it's difficult to take that gallium metal and put atom by atom of it. I'll show you what we do. So let's just see. Maybe I'll share the screen again. Yeah, can you just share the screen perhaps? Maybe it's a good time to just take a look at the chat as well to see if yeah. Okay. So what do we do is we are depositing metals. We are depositing these materials using chemical reactions in a layer by layer manner. So how do we start? What do I use for my gallium? I don't use gallium. I use gallium with 3 methyl groups. Methyl is CH3, methane is CH4. CH3 is the methyl group. So trimethyl gallium. Gallium atom, 3 methyl groups attached to it. For the nitrogen, I start with ammonia. Ammonia is a gas. You might smell ammonia, the chemistry lab. Any public toilet, the smell you get, that's ammonia. Okay. So we start with ammonia, which is a gas. We start with trimethyl gallium, that's a liquid. I'll tell you what we convert everything to a gas. So I'll explain this. It's vapor phase effect. So I'll talk it. But let's look at what chemistry we are doing. So we are taking this trimethyl gallium and ammonia.
Yeah.
And we will heat it up.
Okay.
Heat it up how much?
How much?
Maybe something like 800, 900, 1000 degrees centigrade. Make it hot, really hot. At this temperature, this ammonia breaks up. Okay. So I can get nitrogen from there.
Nitrogen and hydrogen.
And hydrogen. Yeah, I don't care about the hydrogen. I want the nitrogen. Yeah. And the trimethyl gallium also, these methyl groups go away. So when I get trimethyl gallium and ammonia, at the high temperature, these methyls go away. So there's gallium, there's nitrogen because the hydrogens have gone away. So gallium and nitrogen can deposit and form gallium nitride.
Okay.
It's not that easy. The methyl group and the hydrogen, it becomes methane.
Yeah.
That's a gas that can go away.
Yeah. Okay.
So this is how I use it. And if I want to do gallium arsenide, I will use trimethyl gallium and ASH3, arsine. Or if I want to do a phosphide, I'll use PH3, phosphine. If I want to do aluminium nitride, I will use trimethyl aluminum. If I want to put indium, I will use trimethyl indium. So by using these materials, and these are what are called organometallic compounds, organo because of that methyl or ethyl or whatever, and metal because you have gallium, aluminum, indium. So you have an organometallic or a metal organic, and it's coming in a gas phase and it's depositing layer by layer. So you have metal organic vapor phase epitaxy or metal organic chemical vapor deposition. So that's what we do here. Of course, it's not that easy, right? I showed you the final equation, but in real life there are probably some 200 sub reactions that are happening. It's not that easy, but people have figured it out. Chemical engineers are smart guys. They figured out this, chemists and whatever. And we can actually do it layer by layer. The picture you're seeing on your screen, it's actually work by an earlier student, Preeti. She's actually somewhere on this Zoom call as well. She deposited very, very thin. You see that bar in the image? That's 5 nanometers. Remember, your hair is probably 50 micrometers. That's 1,000 times more than your hair. So a nanometer is like 1,000 times smaller than that's 5 nanometers. Okay, and these you can see some diagonal lines. They are layers. The darker lines are gallium nitride regions. The lighter places are aluminum gallium nitride regions. So these were deposited layer by layer. And what you're seeing is a electron microscope image of this. We can't obviously see these very thin layers with our eyes. You can see only an electron microscope image. Can we just have the next one? I'm just wondering what it is. Yeah, just go ahead. Okay, go ahead. No, the previous one. Yeah. So now, of course, this equation is very simple, but I want to really grow high quality materials. I want to grow different materials and make, LEDs and transistors and make devices and, so as a person who operates this machine, what do I change? I can change the temperature. I can change various things, the pressure, the gas I use. So let's now look at, you can stop the screen share. Now, we'll probably tell you a little bit about what happens in this lab over here. So what are we trying to do? We are trying to take trimethyl gallium, react it with ammonia, and make gallium nitride. And what we will do is, we will deposit it on a wafer, on a piece of sapphire. So this is a sapphire wafer. You can hold it near the camera. This is a sapphire wafer. We will deposit this thing. Why do we use sapphire? Well,
can you tell us something about the substrate we use for? I heard something about lattice matching.
Yeah, okay, lattice matching. We're already getting into that. We will do it. We'll come to lattice matching. We'll definitely come to lattice matching. But maybe what we'll do is we'll tell them what all this is.
Yeah.
So right now, let's do one thing. Let's turn the light on. So this. Okay. Yeah. So I think. Yeah, you can just hold it so I can tell you what is what over here. So let's turn that light on also. So we will eventually go there. I'll take it there. So that. Okay. So what we have here, right? This part of the system. This is all chemical engineering. It's all chemical engineering designed to transport the correct amounts of these reagents for the reactions into the place where the reaction will happen. So what we have here are all kinds of valves. It's a maze of valves, pressure controllers, flow controllers, everything designed to mix. So suppose I'm doing aluminum gallium nitride, I need to mix the correct amount of aluminum, trimethyl, gallium. Now, you asked me that trimethyl gallium was a liquid, right?
Yeah.
And everything out here I said will happen from a gas.
Yes.
So what do? How do you convert a liquid to a gas? Well, one thing, you can boil it, you get a vapor. But at any temperature, any liquid, above the liquid, there is some vapor. Some molecules are always evaporating. So what I do is, I have these liquids in a container, and I bubble. Just imagine taking a straw and blowing through it, and you get bubbles coming through the liquid. You bubble a very, very pure gas through it. Remember, purity is everything over here. Which gas?
Maybe.
Well, the only gas you can use, purify, or right now you can purify nitrogen also, but the only gas which you can purify to 99 and then 7/9% pure is hydrogen.
So do we purify the gas here in the
Yes, you can't. Nobody in India sells you 99.9999 that kind of hydrogen. No. But hydrogen is one element which is extremely easy to purify. Not easy, but it's possible to purify. And that's because there is another element that comes to the rescue. This is a metal called palladium. Now, if I have a sheet of palladium and I pass hydrogen gas on one side, okay, palladium has a unique thing that it allows protons to go through it, single protons. Now, of all the elements in the world, how many elements have a single proton? Only one.
Yeah.
Hydrogen. So hydrogen and only hydrogen can go through a palladium cell. The proton goes, combines with another electron, becomes hydrogen again, and goes away. Okay. So a palladium membrane, when it's hot and you can use a palladium membrane to purify hydrogen. So we purify this hydrogen, we bubble it through this trimethyl gallium. It picks up the vapor, and the vapor gets transported from here. Okay. So that's how we transport the vapor, and there are lots of things over here. And then this thing goes into what we call a reactor. It's not a nuclear reactor or anything, it's just a reactor because a reaction happens there, a chemical reaction. Okay. So now maybe we're going to change things, and I'll hold the camera. Let's plug the laptop. We can just keep the laptop there. So we'll have enough things. We are just going to try and show you what happens here. Okay.
So I was wondering, what are these gloves?
Ah, the gloves. Yeah. So, see, remember, I've said purity is everything. Purity is everything, but we are in Mumbai. There's so much dust in the air, so much pollution, so much, TIFR is right next to the sea. There's so much water vapor in the air.
Yeah.
Not good. We don't want all those molecules also.
Yeah.
So, one option is you keep your entire lab super clean and everything. But what we decided is, only the place where the reaction happens, we'll keep it in what is called a glove box. So these big gloves, Rahman is going to just come here and show you how this is used. This glove box has extremely pure nitrogen inside it. Okay, and so whenever we open the reactor, put stuff in, it never sees the Mumbai atmosphere. So we keep it isolated, we keep it very, very clean and very pure by using ultra pure nitrogen.
And how do we put things inside this box?
How do we put things inside this box?
Yeah.
Well, what do you think? We put things inside 10 years back when we built this and we never put anything. No, of course we need to put things inside. Well, it's got something called a load lock. So we'll show you the load lock also later. There's a little door. There are two doors. So there's a region in the middle. You open the outside door you get something in, you shut it. Then you remove the air from it, put nitrogen back. Remove the air from it, put nitrogen back. Do this many times. So now the region in between, which was exposed to the outside air, only has the pure nitrogen gas. Then you open the you open the other one and then take it inside this chamber. We'll show you that. Okay, let me do one thing. Let's 1 second. Let's keep the laptop here. Let's carry that. And I'm going to hold this and try and see what we have. So here is Rahman. He's going to operate the thing, but first let's try and show them what is inside here. Okay, so this thing here, what you're seeing inside here is a reactor, and yeah, why don't you lower it so people can see what is? Good. That's great. So what you see here is a plate.
I see 3 circles.
Yeah. You see 3 circles because this is a plate in which you can keep 3 of these wafers. The wafers we remember we showed these wafers. You can keep 3 such wafers. You can keep 3 such wafers in it, and you want to keep a wafer? Or okay, we can just show them that. And then this whole thing will move up, and below this plate is actually a heater which can heat things up to almost 1200 degrees centigrade, depends on the material we are growing. And what we do is from the top, so you saw this part where the gases are mixed, then the mixed gases come to the top over here and there are tubes through which it comes in. Okay, it's tough to show you that because we'll have to put the camera inside the box, which is inside the glove box, which is going to be tough. But yeah, so this is the reactor actually, where we think you can put it up. So we would load this thing, and then it would go up, and then it'll the gases come from top over there. And what you asked earlier, this, you see this little a little door over here. This is the door. You can open it from this side and get things inside. This is the connection to the outside world. You open that door and get things in. Okay.
Oh, so there is a compartment between.
Yes. So there is a compartment between this place and here. This is the outer door. So you can open this. You open this. You put whatever you want from. So right now we're in the room. This is the access from the room. You put stuff in here. You shut this door, and then you can there are a lot of.
So there is nitrogen inside.
Yeah, there's nitrogen inside the. Now when you open it, there'll be right now there's nitrogen. When you open this, there'll be air inside it. So there's a vacuum pump. You can remove the air, put nitrogen, remove the air, put nitrogen. You do this. It does it automatically, actually three times. And then you move this door. You can open this door from the inside.
After closing
that door. Yes, if you don't close that door, of course, it will not let you do it. And this is what you have. Of course, inside there are lots of other things to clean the place and pick up the. You have to pick it up using some vacuum. You can't pick it up with your hands, right? There's some vacuum. A little vacuum pickup that helps you pick it up. Okay. So yeah, so this is it. And
I do see large bellows coming from the reactor top and going onto the roofs. What are those bellows?
Oh, you're asking what are those? Yeah. Okay. These things at the top of the top.
Yeah.
Okay, and lots of tubes and all around there. Yeah. Okay. So it's okay. It can be there. What is the name of this whole machine? This whole machine is called a metal organic chemical vapor deposition system, or a metal organic vapor phase epitaxy system. Okay. Now, yeah, what are all those things? Now, remember, I said that we have to be very, we need to be very careful about the purity. Everything has to be very pure. But there's another equally important thing. We have to be very careful about safety as well. Did you ever like to smell in a public toilet? No, you didn't, right? So ammonia smells bad. You must have smelled it in the chemistry lab as well. Ammonia smells really bad. But at least when you smell ammonia, it's at a limit that it won't kill you, right? You smell it before the level at which it becomes really toxic or dangerous. But many of the other gases, phosphine, arsine, etc., are very, very toxic. So, you know, if you get poisoned with arsine, it binds to your red blood cells. There's nothing you can do. It doesn't transport oxygen. And the only thing people can do is change all your blood, which is very difficult. So basically, and nobody really knows how it smells, because if you can really smell it, by that time you're dead. So the concentration of arsine that is safe, right, where you can work 8 hours a day, is 50 parts per billion. 50 parts of arsine per billion. Okay. Yeah, that's right. Ammonia, you can work at 25 parts per billion. This is parts per billion. Okay. So 1,000 times more toxic. So now what we have is we need to make sure that under no circumstances can a toxic gas come outside the reactor. Okay, that's one. Now these metal organic compounds we use, the trimethyl gallium, the trimethyl aluminum, etc. These are also fun stuff. You know, they will spontaneously burn in contact with air, and they will spontaneously explode in contact with water. Exactly, right? Fun stuff. So you have to be very, very careful while handling them, and of course, a lot of the design and the expense of such a system, the difficulty in making such a system, is that you need to make something which is absolutely safe. Okay, and we do this in many, many ways. Step one is, you see these big. You were asking me about these big things above the reactor. Yeah, can you just move the camera up to show these? Yeah, big. There are these. You see these two very big pipes that are going up. Well, what we have above in the roof are very big exhaust fans. Remember the exhaust fan in the kitchen? That's like small. Yeah. So that's probably few hundred cubic feet per minute or something. Right. We have two fans of 3,500 cubic feet per minute. So they are just sucking the air out of the room. Okay, now, today we are not operating. We've removed these covers to show you, but otherwise everything is usually blocked off, and there are little slits through which air goes in, because the air is being sucked outside the system. Air from the room goes in. So the idea is, in case a pipe breaks or there is a small leak or something, nothing will come into the room. It will go up into the roof, and there is so much dilution. We are mixing it with so much fresh air that it is, when it goes outside, it's probably going to be below the limit that it's being. Also, we are using hydrogen. Hydrogen is the carrier gas. We are flowing, maybe a few liters of hydrogen every minute. When we are really growing, it could be 20 liters a minute. Hydrogen is flammable. We don't want a hydrogen leak. So we have lots of toxic gas sensors around, flammable gas hydrogen sensors around, and our sensors are so sensitive that of course we will detect a very, very small, again, parts per million leak. But you know where the TIFR canteen is? Yeah. East canteen. Yeah. In the East canteen, sometimes how do you light a gas? You turn the gas on, and then you light a match or something, and you light it and you take it. If they delay a long time, they turned the gas on and they went looking for the match. Where is the match? The gas is going out. We are at least 100 meters away, but we will detect that. Okay, these are extremely sensitive detectors, and our policy is, if we detect anything, even if it is on a level where it is safe to work for 8 hours a day, we will switch on. Things will automatically switch on. Okay. And it's not that. So whenever we use hydrogen, anything which is carrying hydrogen is also connected to nitrogen. The nitrogen pressure is always more than the hydrogen pressure. So even if power fails, right, it is such that the nitrogen will push out all the hydrogen. We don't, the valves are designed such that automatically the power fails, all the nitrogen valves will open, all the hydrogen valves will close, all the hydrogen, all the toxic gases, everything is moved through the system. Right? Even if the power fails. So you have to design your system, and you probably see a lot of plastic pipes also going around the room. Yeah. So all these pipes are connected to these toxic gas sensors. There's a toxic gas sensor continuously monitoring the environment, monitoring inside the lab, monitoring outside the room. And we don't use. You don't ask me how do we turn all these valves on. We'll show you how we turn all these valves on. But our safety logic does not depend on Windows or any software. We don't trust software. Right? Okay. Software can crash. Our safety logic is hardwired relay circuits. Right? They are fail-safe relay circuits. It's probably 100-year-old technology, but it is absolutely fail-safe. There's no software involved in the same thing. For safety, you do not compromise anything at all. Yeah. Okay. So yeah, how do we control the system is a good thing. Maybe we'll just show them the control screen as well. It's almost like playing a video game, right? You see, there's no way to control the valves here. The valves are all controlled by yeah. You can see this computer screen. This is showing you the position of all the valves, and what I can do is I can always let's see. Shut this way. Yeah. So if I is that
not
sound visible?
let's see.
Yeah, just hold it steady. So if I click on a valve, you see it changes color. I've shut it off. Okay, and then if I click on a flow meter, for example, if I click on a flow meter, I can change the value of the flow over here. It's not focused, but still you can see that I can change the value of by clicking on it, and if I send, and it will change the value of it. So it's almost like playing a video game. You can control everything from here. You can also write programs that will control all this thing for you, because if you're controlling 100 valves at a time, you can't do it manually, right? You can't even click, you'll go mad. So you write programs that can actually tell the system what valves to. Okay, so at the end of it, what happened? Oops, no, somebody pressed. What's going on? It's got disconnected. Just as the camera seems to have in this move. Okay, we are back on. We've got the camera back on. Sorry, when we moved the laptop, we disconnected the camera by mistake. That's live. That's what happens. You're live in the lab. Okay, so now what do we do here? What do we do here? What do we make here? How does this thing look? So let me tell you what we do. What do we deposit layer by layer? Okay, let me just quickly show you that. Yeah. So this one of the things a simple thing which machines like this make are what are called light emitting diodes. So light emitting diodes, you may have heard of a diode. A diode is something that allows current to flow one way. A diode requires two kinds of semiconductors, something called a p-type one and an n-type one. Don't worry if you don't know what it is. And the real, the stuff that happens where this p and n-type materials meet. It's called a p-n junction. And at this junction is the sort of secret sauce for the LED, which is, so you have, what do we do? On sapphire, we grow gallium nitride, about 1 micron thick. 1 micron is again 50 times thinner than your hair. So, or 100 times thinner than your hair. If you have nice thick hair, for me it will be 50, for you it will be 100. So then you grow some N-type gallium nitride and P-type gallium nitride, and in between the two is where you have what are called quantum wells. Quantum wells are very, very thin layers of semiconductors. We have indium gallium nitride. How thin? 4 nanometers thin. 4 nanometers separated by 10 nanometers. And this is the region that emits light. And by controlling how much of indium I put in the indium gallium nitride, I can control the color. Okay. So here you see some devices, which we had made. But the beauty of it is we can actually, because it's blue light, which you can see in your eyes, we can actually show this to you right here. So maybe what we will do is, Manisha will show this to you. So what we have, first let's see what we have. What we have is a little piece of semiconductor on which we've made some contacts. We just made some little contacts to it, contacts to the N and the P. And what Manisha has in her hand is a 9-volt battery. Where's the 9-volt battery? There's a 9-volt battery, and she's got some wires. And she'll just try and connect the wires N to N and P to P. And you see it's glowing blue. That is a blue LED which was made in this machine right here. Okay, it's again, the nice thing is, how do we actually wait, let me just see if I can go to the next slide coming up. Yeah, remember that, let me just show you the, I said you want to make LEDs of different colors, right? Now, the simplest way to do it, remember, I have a reactor where it's very difficult to say, okay, put exactly 23% indium in. We can't control the indium concentration so much. The way we do it is by playing with things we can control. And this is again Preeti's work, where just by playing with the temperature, remember I said I can heat this up to 1200. I don't have to do it. That's the maximum. So if I grow something at 725 degrees centigrade or 775 Celsius, it'll just depend. In one case, you get blue. In the other case, you get more indium, you get green. So that's what we do in our everyday research. We are playing with the parameters to try and change the kind of materials we grow. And yeah, and these blue LEDs are super important. If you remember, about 10 years ago, the Akasaki, Amano, and Nakamura, they got the Nobel Prize in Physics for inventing the blue LED, because the blue LED allows you to make white LEDs. Okay, and what I didn't tell you, of course, is how do we make these chips? And I think somebody asked in the very beginning, how do we make these chips? First, you must understand how small are these chips, these LED chips. The LED, of course, you can see it. I mean, if you have a mobile phone, you can see your flash. That is an LED. You can see how small the chips are. What we would do when we grow a wafer. Suppose we had a wafer of gallium nitride or some LED structure which was like this. We would take it to another lab, which is called a clean room, and then we would make devices out of it. We would, put metal contacts, say where does the current go, where does the current come out of, and then put wires through that, etc. And these chips are really small. I don't have LEDs with me. I have something else which was made in our lab, not in this machine, in another older machine. These are lasers, laser diodes, the lasers in your laser pointer, laser printer. They're also very tiny. And how tiny are they? Well, there are many in this box that you don't see. So let me just take some out. There are hopefully some of them here. Yeah, so this is a box. So let me see if I can point. You can see the pencil, and what you see here, not these longer ones are actually many of them. The single chip is the one which is right here. So let me hold my pencil there. I don't know if it's going to focus. These ones which are slightly longer are 2 or 3 chips together. A single chip is right there. There is another single chip. Most of these are bars. It's very I mean, this is something the camera is not even going to pick up. So many of these things have maybe the lines that you see, the little like small things, usually will have about 10 chips on them. So these chips are really, really small. If you want to know more about how we make them, you can ask me later. But let's see something about white LEDs before we.
Yeah.
How do you make white light? Remember, they got the Nobel Prize for making blue LEDs, which enable bright and energy-saving white light sources. Okay, so yeah, let me just stop screen sharing. Okay, so let's see. I mean, you all have mobile phones. All have mobile phones. Mobile phones have these flash. The flash is an LED. First thing, lighting has changed.
That's on.
So earlier you had these big bulbs, right? The bulbs which glow and they get hot, and there's a filament. You can see the filament getting hot, and when I switch it off, you can see it as it cools down. From these bulbs, we went to tube lights, the tube lights which are there in our roof, perhaps. But there are also these compact fluorescent lights, CFLs. Okay, you have CFLs which are they don't get, the bulb gets very hot, it's still hot. You can't touch it. In operation, a CFL is much more efficient. A bulb, 95% of the energy is heat, only 5% is light. Tube lights and CFLs are much more efficient. They probably make around 20% of the energy that they get into light. And even more efficient are LED lamps. These are LED lamps which we use these days. Now, what is inside an LED lamp? If I opened this up, if I took this bulb and I opened it up, what would we find? We have done this for the purpose of science, and what we have inside a bulb is this. Okay, this is what is emitting the light. As you can see, there are many of these LEDs. And what color are they? Are they blue? No. What color do you think they are? Right, they're yellow. Well, here's a bigger bulb. Here's a bigger bulb. And here, yes, Mayank, they are all yellow. Here, they're all yellow. They're all yellow here. In fact, look at your camera phone closely. Look at your camera phone closely. You will see that the LED is yellowish. And if you have a very high-end phone, it might have two LEDs, one of which is slightly reddish. You see, this has two LEDs. One is yellow and one is reddish. Okay. So, but we want to make white light, right?
You want to make
Yeah, we want to make white light. So, white light. What is white light? Okay, white light is a combination of the primary colors. The primary colors are green, red, blue. Now remember, if you're mixing paints, when you mix paints, red, blue, and green give you black. But when you mix light, red, green, and blue give you white. Okay, so we have out here. There are red, green, and blue, and if you go sufficiently far away where you can't distinguish them, it will look white to you. Okay. Now, how do you make LEDs? Yes, you can make LEDs. So let me again share a slide to tell you why these LEDs look yellow, because that's the easiest way to make them. 1 sec. No, 1 sec. I need the screen again. Okay, here we are. What you see is there are many ways to do white LEDs. In principle, the simplest way is to take a blue LED, a green LED, and a red LED. You take 3 LEDs. So this is what we were trying to do here. We won't turn it on. We'll just show you the LED. So here, we had something which had blue LEDs, red LEDs, green LEDs, try and combine them. That's one thing. But that requires 3 different LEDs. Each of these LEDs will require some power supply. So it's not an easy way to do it. Okay. The simplest way to do it is to take, remember, green plus red is yellow in light. So if I can somehow combine blue light and yellow light, here is where you have materials which are called phosphors. Phosphors have nothing to do with phosphorus, the element. Phosphors are something which absorb energy, higher energy light, and radiate slightly lower energy light. Now, blue light has more energy than yellow, green, red, etc. So if I have a material, I have a phosphor which can absorb the blue light and emit yellow light. That's what I need. And that is exactly what all these white LEDs, things have. They look yellow because they have a yellow phosphor. So there is a blue LED underneath this, and there is a yellow phosphor on top. The yellow phosphor, you have to put the right amount. So it doesn't absorb all the blue, then you'll get only yellow. It lets some of the blue through and adds some yellow to it in a way that blue plus yellow gives you white. Of course, the earlier LEDs, the white was very bluish. It was not like daylight. The sunlight is a little yellowish white, little reddish. So now people have started putting other, mix not just yellow, but a little bit of red. You can control the kind of white you get. This is called the color temperature of the white. Don't worry about it. But that's why some of the newer flashes, they have a red. They put some extra, apart from the yellow, they put some red as well. Red is also lower energy. So that the light that you get, the white that you get, looks more like natural daylight white and not the tube light bluish white. Okay, so this is what they do. And all your these little LEDs, even when you see an LED, what is called what is this? A tube light, right? A tube light. Turn it off for a second at least. See this tube light. Turn it off. See, we have cut it open. And when you cut it open, you can see what is there is actually just a row of these small LED chips, and there's a plastic on top to diffuse the light. So we've cut open the plastic here so you can see what is inside the LED. It's basically these very tiny blue LEDs with yellow phosphor that generate the light. Okay, so we are at 1 hour. It is 12 o'clock now. Maybe we should ask.
Can I ask one last question?
You can ask one last question, of course.
So you were telling us about growing layers.
Yeah.
So we can only grow layers in the system.
No. Okay, so let's stop this. So Manisha is asking me whether we can grow only layers in the system or we can do something else. So of course, that's because she works on something else. So Manisha actually makes. You have a gallium oxide crystal here?
I have.
Okay. Manisha works on a different material. It's called gallium oxide. And maybe you can just go near the camera and show them a piece of gallium oxide. She actually grows, not thin layers, but take it. Okay, you'll have to bend the camera down.
No.
Yeah, those glass-like things you see are gallium oxide pieces, and Manisha grows gallium nitride on them. Okay, but not gallium nitride layer by layer. What she's trying to do is grow, you can say, skyscrapers of gallium nitride. Imagine how Nariman Point in Mumbai looks with all the skyscrapers, but imagine that all this was a million times smaller. So she grows what are called nanowires. Nanowires, where instead of growing flat, you put down something which will allow the growth to happen only vertically. So what you have is, you start with a flat thing, and just like grass grows up, you have these wires that are growing up. That's what Manisha works on for her thesis. That's another way of growing things. We won't explain it right now. Let's see what people have asked, right? Let's see, there must be lots of questions by now. It's already an hour. So let's see in the last 10-15 minutes, we can see what kind of questions are there in the Q&A and the chat. How many of them have not been answered? I think many of our lab members and ex-students and friends have been on the chat and have hopefully been helping you with some answers. But if there are some interesting questions that we should take now, we can take, and you can still keep putting in your questions and we will try and answer them. What do we have? Do we have
There is one question. LED lights are bad for health. Is it true?
LED lights are bad for health. I mean, I would say that if it is a well manufactured LED, then you have no problem. The issue is, there are two issues. One is, I remember I told you that the LED is, I'll just hold it near the camera. LED is the white LED is a blue LED which has this yellow phosphor on top. Now, if your phosphor is not completely covering in the plastic on top that they put has this phosphor. If the phosphor doesn't completely cover it, some of the blue light can escape from the sides, right? We need some of it. Earlier, older LEDs, the blue was near the UV. You certainly don't want UV light to come out. Okay. And if you look at any blue spectrum, it will always have a little bit of UV. You want to make sure that the UV doesn't go out. Ideally, the plastic itself should stop it. But earlier LEDs, they had some leaky UV light. Okay. Now, that's fine. That's fine. I'll be sure. Most current LEDs, and this is why you have to be very careful. The very cheap LED you sometimes get from the roadside, they may be sort of products which haven't met the quality specifications. They may leak UV light. That is one thing. The other thing is, we use LEDs to backlight our phones. Our phones, the backlight is an LED light, and we are looking at our phones way too much, especially at night. Now, again, if your LED is putting out too much of bluish light, that is not helping you sleep. It disturbs the sleep cycle. So it's always good, you find on all laptop monitors, phones, you can set this night mode, which makes your screen a bit yellowish. Okay. So what is not good is a lot of blue light at night. Now remember, all people who advertise glasses which are blue stopping and all, if your glass is a piece of plastic, like most glasses today, it will stop the blue light anyway. Most of them will stop it. You don't need an additional coating. The most important thing is, if you're reading something at 10 o'clock, 11 o'clock at night, where actually it is time to sleep, it's best not to look at a lot of blue light. That's the only thing. LEDs by themselves are not dangerous to health. I mean, you're not supposed to eat them, of course.
YouTube is clear.
Somebody is asking, sapphire is a gemstone consisting of many elements like titanium and others. Why we are using it for gallium nitride?
Sapphire is a gemstone. Can you put the camera down a bit here? So, Manisha, you can also come. You can also answer questions if you want. Okay. Yes, sapphire is a gemstone. All gems, just like I said, semiconductors are useful only when you dope it with these very small atoms, small amount of atoms. All gems are useful or colorful, except diamond probably. But even diamond, if you want color in diamond, it comes only because of impurities. So, yes, if you want ruby is sapphire with chromium atoms put into it. Okay, so sapphire is aluminum oxide, crystalline aluminum oxide. Crystalline aluminum oxide is transparent, pure sapphire, has no color. Yeah. However, once you put in all these crystals, if you put ruby, it will become red. If you put that's chromium, right? If you put you do it. Yeah, why sapphire? Remember aluminum oxide, the same. This go down group 3, aluminum to gallium. Gallium oxide is also like sapphire. You saw these things, and show the camera. And Manisha's thesis is looking at putting vanadium in it. Vanadium, and once you put vanadium, you can see that it's green in color. Right. In fact, that looks very much like a piece of emerald, I would think. You have one where you can take it out and hold it or something. Or take this. This probably looks easier to show.
Right.
It fell down. It's a bit tough to. No, it's reflecting the work. Yeah. Take it out. Take it out and hold the camera. Just bend the camera down. Yeah. That might be tough. It's transparent, so they won't see it. Put it in the keep it on the white thing and just bend the camera down. Yeah.
Yeah.
There, you see, this is greenish. This is vanadium. Okay, this is vanadium doped gallium oxide. Similarly, when you have sapphire, which is doped with other elements, that's when you get colors. Pure sapphire is transparent, and this is not naturally occurring sapphire. These are artificially grown crystals. You can grow large, cylinders of sapphire, and then you can cut them and make crystals. You can get even this big discs of sapphire. We use 2-inch. Our system takes 3 2-inch wafers, but you can get sapphire. And sapphire actually, it's used because it's probably the cheapest material that you can grow on. This 2-inch disc of sapphire costs maybe $10 US if you buy it in bulk. Gallium arsenide would cost $100 US approximately, order of magnitude. If you had silicon carbide, that would cost $2,000 US. And all materials, if you want, are you can make them, you can get substrates, but they are much more expensive. So we use sapphire. It's also all these materials, all the compounds, they have a certain crystal structure, right? Some crystals, like salt crystals, are cubic. Gallium nitride happens to have a hexagonal unit cell. Sapphire also has a hexagonal unit cell. So it's easier to grow something which is hexagonal. Imagine your pencil on something else that's hexagonal, rather than to grow it on something that is cubic. So you have a lot of things that come into deciding how you choose a substrate for deposition. Sorry, long answer. Are there other questions on YouTube or Zoom? I can see somebody typing a question, but I can't read it from here. That's Ashish typing an answer, I guess. Ashish, Preeti, Ullas, if you guys have seen some good questions which you have typed the answer to, but you think other people might also be interested in that question, we can answer those questions live as well.
Arnab, can you hear me?
I can hear you, yes.
Oh, great. So there is someone, Mayank is asking, are there any bulbs more efficient than LEDs in the modern world?
Are there bulbs more efficient than LEDs in the modern world? The simple answer is no. As of now, LEDs are probably the most efficient sort of sources of general lighting. people are trying. So in an LED, what do? You have a blue LED exciting yellow phosphors. For very specific applications, remember a bulb, you want light everywhere in the room. For very specific applications, for example, car headlights, where you want light mainly just in front, people are trying to make lasers, semiconductor lasers, which will excite phosphors and generate white light. They may be more efficient, but we don't know about them as yet. They're not at least available everywhere. So that's the short answer. As of now, LEDs are very efficient. Almost, you can get 40-50% efficiency. May not be in the final product, but at least on the LED chip. The most efficient light source, semiconductor, like any light source, the most efficient light source is a semiconductor, a laser. A laser can get up to 60-70% efficient in terms of light to electricity to light conversion. Okay. Any other interesting questions?
And how does the efficiency of LEDs compare with CFLs?
Okay. So remember, light bulb, incandescent lamp, 5%, CFLs, 20%, 15-20%, very high efficiently designed, 25%. LEDs are 30-40% or more, heading to 50% these days. You can get LEDs which are commercial LEDs. So when you buy a bulb, right? You buy any bulb, tube light, LED, whatever it is. Look at the package. Look, dabba pe likha rehta hai. What is written? How many lumens per watt it gives you, and what is the efficiency? So the what you need to compare is lumens per watt. Okay, and now even the commercial LEDs give you more than 100 lumens per watt. Okay, you of course need lots of lumens to read and write and whatever else. So if you need, say, 500 lumens or 700 lumens, that is, you can get it from a 7-watt LED. To get 700 lumens from a light bulb, you need a 60-watt light bulb. Okay, what else? Yeah.
Okay, great. And there's one question, if you have already answered, I don't know. Gautam is asking, what is the name of the whole machine behind you?
Yeah, the name of the whole machine, again, I said, is a metal organic chemical vapor deposition system, MOVPE, or also called a metal organic vapor phase epitaxy system, MOVPE. They're the same thing.
Okay, so which company makes the best LEDs?
Which company makes the best LEDs? I don't think there's any one company that makes the best LEDs. I would say that there are two kinds of so in Taiwan and China, mostly there are companies that are making billions and billions of LEDs every day, billions and billions of these small LEDs every day, which are meant for mass market lighting. There are also some companies who are, I would say, at the forefront of research in LEDs, where like if 100 lumens per watt is what is available in the market, they're already at 300 lumens per watt, or higher than that. So those companies are companies like Cree, CREE, Nichia in Japan, Lumileds. There are some companies in the world that are probably the leaders in research. Osram. There are many companies exploring different physics to make LEDs.
Okay.
What I haven't spoken about today, and it would unfortunately need a lot of physics, is to try and tell you why LEDs are still at 50% efficiency. That depends. That to do that, we would need a lot more physics, which would be difficult to just do here. But maybe someday we'll talk about that as well.
Yeah, that's a whole lecture in another.
Yeah, that's a whole lecture by itself because the LED by itself, indium gallium nitride, the material has lots of defects. It's not the best material. Not the most perfect material. Crystallinity wise, not the most perfect material. The LEDs, this material has got internal electric fields that are trying to push the electrons in the wrong way. So there are a lot of things which we are trying to improve and come up with new materials for these devices as well. Okay,
Arnav, there is a very nice question. Okay. Is there any biodegradable material which can be used to make LEDs? And also, this was asked by Shubham. And Meeta Das is asking, does disposal of some LEDs cause biohazard? So these two questions are related.
Are there biodegradable LEDs? Okay, so first thing, the LEDs I spoke about, most of the LEDs in the market are inorganic LEDs made from gallium nitride plus phosphor or whatever else. These are all, they are not biodegradable. Okay. However, I told you chemists are smart people. They helped us make this chemistry that does this. They can also make plastics that emit light. Okay, these are called organic LEDs, OLEDs, OLED, and you may have seen some high-end phones, Samsung OLED screen or AMOLED screen, active matrix, organic LEDs. Organic LEDs are basically plastics or organic molecules that emit light. These can be made biodegradable, but they are still a very small fraction of the total LEDs around, simply because we haven't solved the main problem with plastics is degradation. They degrade. You keep a plastic bag out in the sun, it degrades after a while. Now, these LEDs also have the same problem, except nobody keeps a phone for 10 years. They'll get a new phone. So before the screen degrades, they'll actually get a new phone. So for phones and things like this, it's okay. But they're still not at the power level that you can really make bulbs out of them as yet. They're good for displays where they are spread out, not concentrated sources of lighting. So not yet. Is there a safety hazard with disposing LEDs? Not so much in the gallium, indium, aluminum. Sometimes the materials used for wires and contacts, etc., may be the problem. The solder used, after all, when they make an LED, when is an LED? When they make LEDs, they have to be soldered to the printed circuit board or soldered to whatever the backplate is. So, that is more thing. But compared to tube lights, remember, tube lights have far more dangerous for the environment chemicals inside them than LEDs do. But yes, LEDs are not biodegradable.
Okay. Arnab, does cooking in high temperature probably result in a tasty semiconductor? No, sorry about that. This is just a joke. I mean, you showed some very high temperatures in your machine.
So, well, the temperature depends on the material you're growing. So, if you want to grow indium nitride, indium phosphide, indium gallium arsenide phosphide, you will grow them at perhaps 650 degrees, 700 degrees max. Sometimes indium nitride is 530 degrees. If you want to grow gallium nitride, it's higher. It's 800, starts at 850, 900, 1000, 1040. That's the normal temperature. If you're growing aluminum nitride, that likes to be hot. Aluminum nitride grows at 1080, 1100, 1150 degrees centigrade.
Wow.
There are newer reactors which can go up to 1400 degrees centigrade. So it depends on the material. Generally, when you go down the periodic table, temperature goes down. You go above in the periodic table, temperature goes up.
Excellent. And if you can take a brief question, Gayatri Savarkar is asking, what's the difference between a normal LED and a laser diode? They both emit light, but how does a laser diode get so nicely focused?
I was prepared for this. Okay, and this will be the last question because we are at 12:15ish already. I was prepared, so let me just see if I can. Shit.
The answer to this question would be a bit long, I think.
So I'm going to try a very, very simple answer to this question. I don't know what level the person who's asking the question was at. See, both these tiny chips. You saw these tiny chips for the LED. You saw the tiny chips for the laser, which I showed you. They are all made from the same semiconductor. Okay, you can make them from the same gallium arsenide. The biggest in an LED, the light goes in all directions. So light is going everywhere. A laser, the light output is very directional. And how is this done? This is done because any laser requires mirrors. So you have a source of light, you put it between two mirrors, the light bounces back and forth. So the the concentration of light, the concentration of photons goes up. Only then you can make a laser. Okay. And one more thing is, LED is it's blue, but it's still not a single wavelength. Okay, it's blue, but it's probably got different colors spread out over, say, 10 nanometers in wavelength range or something, 20 nanometers. That an LED, the light, the wavelength of the light, the color of the light is much purer. It's either A gas laser can be single wavelength. A semiconductor laser can be single wavelength, but it'll have very, few very closely spaced wavelengths. But it'll be within 1 nanometer or 2 nanometers, very closely. So there are two things: light going in all directions and the purity of the color. Whether it's single color or it's got a little bit broader spectrum of light that's coming out. So these are sort of the two main differences between the LED and the laser. There's another. If you can see the screen, the plot below on the left says LED and then laser. So all lasers start off as being LEDs. When you first put current, initially the light is going everywhere. This is a process called spontaneous emission. There's a certain threshold current. There has to be a minimum current. Once you cross that current, then the laser action starts and then the light output suddenly increases. So the brightness of a laser is also much higher than that of an LED, because brightness depends on how much light is going into some angle. Okay, so I think I will restrict it to that. So let's stop the share again. And before we end, I hope there are no more really important questions. Let me tell you about what's coming up. Remember, this was a special Chai and Wai Azadi Ka Amrit Mahotsav. We did this from TIFR. Our standard Chai and Wai session is the first Sunday of the month. That's next Sunday. It will be at Prithvi Theatre, where Sneha is going to take us in the world of biology, looking at mitochondria. This is an in-person session, Prithvi Theatre in Juhu in Mumbai. We will also be on YouTube for this one. Of course, on YouTube, this is a proper Chai and Wai session where there's chai. Today there was no chai. We're in the lab. No food allowed here anyway, and it's online. So we're going to have mitochondria, which we know provide energy, but they do lots of different things in the cell. That's what's coming up next week at Prithvi Theatre. The mid-September session, if you remember, September 15th is Engineers Day in India. And we will be celebrating Engineers Day on September 18th at Vapour College, again in person. We will have Dr. Satyanarayana. Satya will talk about the physics and the engineering that goes into making detectors for doing high energy physics experiments. So these are the next two Chai and Wais coming up. Please do join us. If you're in Mumbai, we'd love it if you come in person so that we can have a discussion over a cup of chai. Thanks very much. I hope you learned something from it. If you have more questions, no worries. Send us an email. Our email address is outreach, outreach @tifr.res.in. We'd love to hear from you, and maybe one of these days, some of you can even come and visit our lab. It's much more nice if it's here. So let me thank Manisha and Rahman for really putting this thing up together in the lab today, and all our colleagues from the lab who've been in the background, and the colleagues from the outreach team who've been answering questions, students, ex-students, everyone who's here. Thank you so much, and thank you, audience, for watching us. Stay tuned to Chai and Wai.
Thank you. Thanks a lot, sir.
Ullas, you can end the